Hello, I'm Kwangwoo, and I'm a PhD student at Iowa State University, and I'm working with Dr. Kazim Wang. Today, I would like to present evaluation quality of 3D printed clay objects using a 3D structural light scanning system. 3D printing technology has been increasingly used in many fields such as medicine, food sensing, and architecture. However, lack of method, guidelines, and specifications for measuring and quantifying the quality of 3D printed objects is one of the challenges in the application of 3D printing technology. Moreover, it would be really difficult to measure the geometry or printing quality when clay or concrete, which requires some time to solidify, are used to print an object. It would be fine when they are solidified. However, when they are still in the fresh state, physical touching might occur during measurement. Therefore, in this study, we used a 3D structural light scanning system called a 3D SLSS, which is non-destructive and touchless tool to evaluate the printing qualities of printed objects. It consists of a camera and projector. The projector projects coded fringe patterns on the surface of the object, and the camera captured the distorted patterns due to the geometric variations on the surface of the object. After determining the camera-projector correspondence pair using MATLAB, 3D geometry is reconstructed. So the objectives of this study is first to explore the potential of 3D SLSS application in 3D printing quality evaluation. Second is to develop a test protocol for 3D scan and image analysis. Third is to identify parameters that govern 3D printing quality. And lastly is to quantify the printing quality of samples. So in this study, we used the commercial clay to print a cylindrical object. We placed the clay in the extruder tube and assembled it with the piston-type stepper motor. Then the clay will be extruded from the nozzle. Then we prepare 3 samples with different printing parameters. There are many printing parameters which significantly affect the printing qualities. In this study, we considered printing speed and extrusion flow rate as main factors. So standoff distance, layer width, and layer thickness were fixed, and we only changed the printing parameter, printing speed and extrusion flow rate. After printing objects, 3D SLSS was installed to capture the 3D images of samples. We captured 4 different side view images and 1 top view image using the 3D SLSS. So for example, at the position 1, 5, 9, 13, we took side view images, and this is one of the example image of 3D reconstructed images. Then we vertically sliced the 3D images, and we had this 2D plot. From this 2D plot, we could measure the layer height, object height, each layer thickness, line of surface profile, and surface angle. Similarly, we could capture the top view 3D images, and same as the side view, we vertically cut the 3D images of top view image, then we could get this 2D plot. So from this 2D plot, we could measure the layer width and the diameter of the sample. In addition to the surface angle, in order to quantify the degree of distortion, we measured the semi-cross-sectional area. Since we knew the line of surface profile and central axis, we could calculate the semi-cross-sectional area. And here is the 3D reconstructed images of samples using the 3D SLSS. The color differences represent the distance from the surface of the object and then the equipment. For example, the yellow color represents the closest distance from the object to the tool, and the blue color means the farthest distance from the object to the 3D SLSS. Visually, we identified that sample 1 shows the relatively good printing qualities. However, sample 3 shows the poor printing qualities due to the distortion at the lower layers. It indicates that the combination of printing speed and extrusion flow rate significantly affected the printing qualities. From the side view images, we had 16 2D plots. Then we call them as a surface profile of sample. As mentioned earlier, sample 1 showed quite good printing qualities. However, small distortion was observed in the 13 to 16 2D plots. Compared with the surface profile of sample 1, sample 2 showed more distortions, and sample 3 showed the biggest distortion among samples. So from the 2D plot result, we calculated the object height, outer diameter, layer thickness, and layer width. The orange color represents the designed value, and the blue color refers to the measured value. It was found that measured values of all samples did not reach to the designed value except for the layer width. It might be assumed that the extruded clay did not reduce the weight of layers deposited above and they deformed. Therefore, relatively the layer width increased and it resulted in the distortion. Then we measure the surface angle and semi-cross-section area to quantify the degree of distortion. If the printed object were printed perfectly, the surface angle should be 90 degrees and the semi-cross-section area should be equal to 1,200 millimeters square. In this study, the differences between the designed value and the measured value corresponded to distortion angle and distortion area, respectively. As listed in this table, all samples showed a certain amount of distortions in terms of distortion angle and distortion area. Among samples, sample 3 showed the highest distortions. Then we developed an integrated evaluation method to quantify the printing qualities of 3D printed objects, considering all test results, including layer width, layer thickness, object height, object diameter, distortion angle, and distortion area. It consists of 6 axes, and each axis corresponds to the percentage of differences between measured and designed values. And the enclosed area was used to evaluate the printing qualities of 3D printed objects. For example, the area is near to 0. It means that the quality of sample is near to what was designed. Based on this evaluation method, it was confirmed that sample 3 has the largest area, which means it has the poorest printing qualities among samples. So here's conclusions. Those samples studied had measured values equal to the designed value, although those appear well printed. Therefore, it is important to identify the key parameters and quantify the printing qualities. Second is printed clay samples generally show the reduced total height, diameter, and layer thickness and measurable distortion. This is mainly because the fresh printed clay material deformed under weight of layers above. And the 3D SLSS provided accurate measurements for geometric parameters and well quantified the degree of distortion of 3D printed products. This method can be extended to quantify the 3D printing quality of cement-based materials. Thank you for your listening.
Thank you very much.